So, we saw one example where we have taken from kinetic example and then we have developed the equations. We also just showed you an example with PEM fuel cell and said it's possible to derive the equation for that. It's going to be complex, so I didn't really spend time on that. So, now I want to summarize and also make some remarks. So far what we have seen is, if you are given a mechanism, how to get the expression for impedance, how to get the expression for steady state current values as a function of potential, DC potential, how to get the expression for impedance at any given DC potential for any frequency, we can calculate the impedance. But in real life what happens is, we get impedance data. We can get impedance data at different potentials or different DC currents in certain cases, like fuel cells, batteries, people usually use galvanostatic mode, different DC currents which correspond to different DC potentials. Galvanostatically one can get impedance data, potentiostatically one can get impedance data, and from that we want to first identify or propose a mechanism and say that this mechanism is an operation and we are getting the impedance data like this. We also have to come up with kinetic parameter values and say, if I use this mechanism and this parameter value, this seems to match the impedance spectra at different DC potential. This seems to match the DC current at different DC potentials. Therefore, I think this is the mechanism. So, first you have to be able to come up with the mechanism, vary the parameter values and see which parameter combination matches this well. If the mechanism you propose and the kinetic parameters you try, if they do not match, either we have not done a good optimization or this is not the right mechanism. Both are possible, right. Sometimes you should be able to tell this mechanism will not work no matter what, no matter how much optimization I do. That I think at this level you should be able to tell that, at least in some cases. If you see 3 capacitive loops, you should not try a mechanism with one adsorbed intermediate. So, certain mechanisms you can eliminate and say this is not possible. Certain mechanisms you may not be able to eliminate, you will have to try, and sometimes we have come to conclusion saying this mechanism, although it has 2 adsorbed intermediate and impedance shows 2 loops or 3 loops, 2 loops for the Faraday, we still cannot predict it with this, because certain features in the potential dynamic polarization cannot be matched with this. Okay. So, that is one more level, just like saying if the data looks like a curve, I can't use linear, but you have to do with little more care to say, can I use quadratic, can I use cubic, should I use sinusoidal wave. Some more analysis is necessary, some more familiarity with this, what type of expression, what type of mechanism can give rise to what type of impedance spectra, that is necessary. The difficulty in using this methodology is that at least I am not aware of any software that can do this, commercial software or free software where you can download it and click it the way you do it for electrical circuit. Electrical circuit commercial softwares are there, even free software is there, where you can give variety of RC combination, RQ, RL, add those things in parallel in series, and to reasonable level, at least for relatively simple data, you will be able to get proper results, proper match. You do not have something like that equivalent one for mechanistic analysis. You will have to write the code yourself in whichever language or script you want to use it in. That is a barrier. First barrier is whether we are able to write the impedance expression for a mechanism that we give. I think at this level you should be able to do, with practice you will be able to do with comfort. Right now you may be able to do it with some difficulty, but next level is to write a program to do this, that is one difficulty. After that, I want to show you some of the challenges, some of the points that you should be aware of when you are actually using it. Okay. There are few I have listed here, I will go through them one by one. Okay. It is easy for us to look at the EEC and learn few points. Let us say we have a circuit shown here, you have one representing R solution, one representing double layer, 2 Maxwell elements, Maxwell element is R1C1, R2C2, all in parallel with RP. It is one representation, you can do similar one in white, does not matter, white or a ladder with inductance, Right now I want to show you what would happen if you have the values given here. Solution resistance is 0, double layer has some typical value and other values I have made them up. If you have data like element value like this, and if you generate the spectrum from 10 power 5 hertz, that is 100 kilohertz to 1 millihertz, you would see a spectrum like this. It is easy for you to do this in MATLAB or any other programming language, calculate this or use commercial software, simulate it, you will get this. So, right now believe me or trust me when I say you will get a loop like this. Now, with this you can tell I need a circuit with 3 time constants. One time constant comes from CDL and RP, other 2 time constants come from R1 C1 R2 C2 or an equivalent representation in any other form. RL maybe with negative values, maybe in void circuit, ladder circuit, you can get this. If we choose that we are going to use, if we decide that we are going to use Maxwell circuit with capacitor, this will do the job. Now, the same circuit, if I had taken data only until 1 hertz, okay, let us say below that for whatever reason it was noisy or it was scattered. So, we decided we are not going to look at this, our spectrum will show only this. Okay. What it means is from this you would come to a conclusion saying a circuit with one Maxwell element can model this adequately, that is probably correct. It does not mean the spectrum was generated from a circuit with one Maxwell element, it is generated from a circuit with 2 Maxwell elements, but we have a limited range of data for whatever reason, noisy data or instrument capability, whatever. This is one example. If I use other values, you might see even up to 1 millihertz I will see only 1.5 loop. To get the second loop or third loop, I will have to use it till maybe microhertz. I may not have enough time to do the experiment, I may not have enough quality of data, even if I have time it may be noisy, scattered, so I can't really see anything, it is or points are all over the place. So, you may get fewer number of loops than the number of time constant in the actual system, because we have a limited frequency range, that is a possibility. Similarly, this is easy to see here because it is easy to generate here. If you have 2 adsorbed intermediate, 2 Maxwell element will be suitable, but you may not see 2 additional loops or 2 loops for the Faradaic process because we have limited frequency range. Second, I want to change the number. So, instead of 300 microfarad, so I have given values like R1 is 400, C1 is 20 millifarad, R2 is 400 ohm centimeter square, because it would be corresponding to a electrode. If it is pure resistance, it is going to be ohm and microfarad or millifarad. C2 was originally 300 microfarad, but now I changed it to 20 millifarad. Now, look at it, R1 C1 and R2 C2, they are matched, R1 is equal to R2, C1 is equal to C2. This case the time constants are identical. If it is close enough, it will overlap, and actually when you measure data there will be some noise. If I use identical values here, I can go till 1 millihertz, I will still see only 2 loops. There is no way I look at this data and say this comes from a system with 2 Maxwell elements or 3 time constants, because the time constants overlap. Even if I go to 1 microhertz, I will not get any difference, I will get only 2 loops there. So, adsorbed intermediates will give you time constants, different DC potential they will give rise to different time constants, and it is possible that at some specific DC potential 2 time constants are overlapping, maybe identical, that may or may not happen that easily, but they overlap and within noise level you may not see a difference. So, even if you go to low enough frequency, you may not see all the time constants manifesting as different loops in the complex plane plot. So, generally if you see certain number of loops, so here if I go to 1 hertz, I will see only 1 loop. So, if I see fewer number of loops than what I should expect in theory, that basically means time constant may be overlapping, the frequency range may be limited, and both effects may play a role. So, when we say either shorter frequency range or overlapping time constant, we will get fewer number of loops than expected. Expected meaning what I would expect in the maximum number of loops from this system. So, if we see certain number of loops, you should say one loop is meant for the double layer in parallel with polarization resistance in the Maxwell representation. Other loops represent how many number of adsorbed species are there, but this tells you minimum number of adsorbed species that is necessary. It does not mean the system has only that many number of adsorbed species. So, if I get a spectrum like this, for example, I can get one DC potential, I might get spectrum like top, another DC potential I may get spectrum like this. It means I need minimum one species as per this, but I might actually require more number of species to really model this data. So, the number of time constants is based on the number of adsorbed intermediates, and this is assuming there is no mass transfer, there is no solution resistance, etc. We can use RMA to eliminate few mechanisms. Okay. For example, not all mechanisms will give you negative resistance. So, if you see negative resistance, if you see polarization data, okay, I am going to draw it here, increasing with potential and then decreasing after some time, current increases and decreases, then you can say certain mechanisms will never give that type of polarization. So, you can eliminate those. Certain mechanisms can give an increase and decrease. So, you should evaluate those. EAR can give you, catalytic mechanism can give you. Okay. There are few other mechanisms which can give, we do not have time to go through everything. So, we are leaving it out, but once you become familiar and try few mechanisms, you would know which can give you a polarization curve which can match the data. Now, I cannot guarantee, even if I find a mechanism and a kinetic parameter set which matches with the experimental data, I can't guarantee that this is the best mechanism. Just like if a quadratic equation works, cubic equation will definitely work. Likewise, any mechanism you find, a superset of that mechanism will always work. Meaning, I find a mechanism, I say first reaction is reversible, second reaction is irreversible, it matches. If I say second reaction is also reversible, definitely it will match. If I add one more step, definitely that should be able to give me a match. So, I can always say this is a mechanism that can describe this data, it is possible. I need to come up with other reasons to say why it can't be something else. Maybe I will use surface characterization and say only these intermediates are found. So, another intermediate may not be necessary to describe this. I do not find any evidence for other intermediates. So, I should not use other intermediates. I can't use impedance data and polarization data and mechanistic analysis and guarantee that this is the mechanism. I can say this is a possible mechanism. Now, when I say I match the experimental data, what I would do is predict data, find the difference between the experimental data and the model data, and when I minimize it, I will say this is a good data, good match. Ideally, it will be 0 error. Now, I have to decide what form to use. Impedance comes in the form of Z real and Z imaginary, that is one. It comes in the form of magnitude and phase, that is another representation. It comes in the form of admittance, again real and imaginary, magnitude and phase. So, should I minimize the error between the real parts and imaginary parts? Should I minimize the error between the magnitude and phase? Should I minimize the error between admittance, or should I minimize it in the impedance form? Ideally, what you should do is prediction, you can predict in any form and change it, it is not a problem. You can predict as impedance, then convert it to admittance, or real and imaginary, you can convert it to magnitude and phase. What way do we measure it? If you are using FFT analyzer in potentiostatic mode, usually that means we are measuring magnitude and phase of Y, that is admittance. You are applying a potential, you are getting a current, the transfer function is admittance actually. That is why in potentiostatic mode, ideally you should use KKT in the admittance mode. But many times impedance mode also seems to work because it is stable under galvanostatic conditions. So, we typically use impedance. Similarly, if you are measuring in galvanostatic mode, you should find the error between the magnitude of the impedance in the model and experimental, and likewise you should do the difference in the phase. If you are using lock-in amplifier or any instrument that uses cross correlation technique like the Solatron FRA, you would be getting real and imaginary parts. That is how it calculates, and again in potential static mode it will calculate admittance, in galvanostatic mode it calculates impedance. Having said that, typically most researchers including our group end up finding the difference between the real model and real experimental impedance, and likewise take the imaginary part of the impedance and find the difference between the predicted and the model values, predicted and the experimental values, and minimize that. You can also use a weighing function, weight factor. Okay. High frequency data gives you information on the solution resistance, high frequency data gives you information on the double layer capacitance, and that is usually not that difficult to find. The low frequency, mid frequency data contains information about the reactions. Okay. You have to give weight for this. If you give no weights, that is unity, you just minimize the error between Z real and Z imaginary, give equal weight to all frequencies or all impedance values, then usually the low frequency impedance will be large value and that has more scatter, and that will dominate, because a large difference in even 1% difference in the low frequency, the model will be here, experimental point will be here, and in case of the high frequency data, even 100% difference will make it only slightly off. So, you need not always give unity weight factor, that may not be appropriate. Again, ideally what one should do is to repeat experiments, 3 experiments, 4 experiments, 5 experiments, at each impedance value find the standard deviation, okay, call it as sigma. Take the inverse of sigma square, that is variance. If you have very low sigma, you have more confidence in the data. If you have large value of standard deviation, you have poor confidence in the data. So, take the inverse of sigma square, that should give you how much weightage you should assign to that data. So, that will be the ideal way to do that. Okay. You can say that I can use inverse of impedance mod, inverse of impedance square, inverse of the real part for the real error, imaginary part for the imaginary error. People have tried variety of these things, various methods have been used, but this is something you have to choose. When you write the code, you have to say how much weightage am I going to assign for each point. Okay. Sometimes at lower DC potential with respect to open circuit potential, data will have lower scatter, because the DC current will be low, corresponding impedance will have relatively better quality. When you go to potential which is farther away from the open circuit potential, there will be large current and associated will be large noise. So, you may have poorer confidence in that data. So, you may not want to give a weighing factor only based on the frequency. You may also want to say at this DC I have more confidence in the data, at that another DC potential I have less confidence in the data. So, I will assign less weightage to that, because you are going to fit all the data using one set of kinetic parameters using one algorithm. So, you have to choose the weight factor correctly. Always you should use potential dynamic polarization and impedance data. Okay. So, you have data of potential dynamic polarization. If you imagine you have one column of DC potential and DC current, then you have few spectra. At one DC you have frequency, real, imaginary impedance, another frequency, real, imaginary, another frequency, real, imaginary. So, you have two types of data, one is DC current and potential, another is impedance, which is a coupled quantity. For each frequency you have one, and for each DC you have one. How do I combine all these errors? I can't just find the model impedance error, that is in ohm centimeter square at different DC potentials and different frequencies, I can calculate the error, I can assign weight factor for this, and then I can't sum up that error with this error. This is a completely different type of data. So, what we end up doing, there are different strategies of using it. Okay. What we end up doing is to minimize the error in EAS, and we give a constraint saying vary the parameter, minimize the error here in the impedance data as per our weight factor, while maintaining the current within certain percentage of deviation, 5%, 10%, you have to choose that. Ideally you want to say 1%, but then you may not be able to find any fit here. So, you will have to loosen it a little and see if you can get a good fit here. So, we write it using MATLAB code, we sometimes get initial values using C++ code. We try like a few billion combinations and then see whether any of them give any data which looks like the experimental data. That if you do it in MATLAB, it takes a lot of time. So, initial values are important. So, after getting some reasonable initial values, what we do is fit one EAS data using MATLAB code and give a constraint here. Okay. You should not give this as a final choice, meaning you cannot use one EAS data to model a system, because you will get infinite number of solutions in theory. In practice, because this program does not know this is a nonlinear system with infinite number of solutions, it may converge to some solution and give you a solution. Because you are using potential dynamic polarization data also along with this, it is okay, but you should use a minimum number of DC potentials, you should have certain number of spectrum, and I will also describe how to get that information after this. But in the beginning we use one spectrum, then we get initial values, we get the fit here, use that as initial value for the next iteration where we add the second spectrum data also, and say fit both of them with the constraint, add the third spectrum data also, and likewise we do it for, in theory I can give all the spectrum data, potential dynamic polarization data, give it to the program and say find the best fit here within 5% of variation here, but it does not seem to work. It will not converge properly. So, we have to take it step by step. So, we minimize the error in real, experimental and model, allow few percent variation PDP and keep adding more EAS data. Another strategy, people have tried this or used this and published with this. For each EAS data they would get a spectrum, and I am sorry, they would get a parameter, and they would find a current value at that parameter, at that DC potential for those parameters. So, if I have a current like this, I have taken spectrum here, spectrum here, spectrum here, just fit this alone, this alone, this alone along with these 3 points for the current. Then see if I can find a relationship between these 3 parameters. So, I will not fit it for K10 B1, K20 B2, instead I will just fit it for K1, K2 etc., and then see if I can relate this with an exponential form or any suitable form. But I do not think it is a good idea, because you do not know, you are not predicting the current at the intermediate values. So, in one case if I predict only 3 points, it may go like this, it may go like this also. Just by fitting 3 points I am not able to say with confidence that the entire curve will match correctly. And getting 3 k values and expecting that all of them will go through an exponential form, or even fitting them with 3 points, I should not fit it to K10 e power B1e, because it is basically doing regression with 3 points. You will get a value, but it is not necessarily good. If you want to do regression, you should do with many number of points. Similarly, K2, K3, all those kinetic parameters, in my opinion it is not a good idea to do. There is a third possibility, it is easy to fit the impedance spectrum to EEC, and it is possible to relate the kinetic parameters to EEC parameters R1, R2, R0 etc. So, we can write the equation, and if you look at it, it is very elegant. You can take a spectrum, it has 50 points, 100 points, whatever number of points. You have 3 spectra, fit it to Maxwell elements, So, you get only 5 data points from that. You have 50 points, you are reducing it to 5 with 2 Maxwell elements. Then kinetic parameters can be related to this very easily, but when you actually try this, you will face problems. 1. All spectra may not show same number of loops. So, in one case you will fit it to 1 Maxwell element, another case you will fit it to 2 Maxwell elements. Same system at different DC potentials, it may show 2 arcs here, 3 arcs there. Now, it is going to be a problem, because your equations relating kinetic parameters to Maxwell elements, it will expect I have 10 kinetic parameters, I am going to map it to 3 or 5 Maxwell elements. In some I have only fewer numbers, in some I have full set, that is going to be a problem. Second, okay, let us say you have actually same number of loops everywhere and you are fitting it to same number of Maxwell elements. We are not using PDP data, potential dynamic polarization data, or you will have to alter it and put that as a constraint. The actual problem is in the Maxwell element, if you change the value slightly, the spectra may change a lot, very slightly. Instead of 1.5 millifarad, if you use 1.6 millifarad, it may change a lot. So, you might think, okay, I am using kinetic parameter, mapping it to Maxwell element reasonably well within few percentage, but the spectrum predicted by that kinetic parameter can vary or can be very different from what is experimentally measured. So, you have experimentally measured data, fit it to a circuit, kinetic parameter mapped to circuit, and I am mapping it almost correctly. It does not mean I will map the kinetic parameter to the spectrum almost correctly, because it is very sensitive. Slight changes here can alter here, and that means I have to get a perfect match here, and that is not going to happen. So, we have tried that method, we have not been successful, and these are the problems we faced. And this seems to work, if at all it works, it will work when you have one intermediate species. If you have two intermediate species, you will get a headache, and this is the headache. Let us say we are able to map the data very well. The experimental data is matched exactly with this spectrum with this circuit on the left side. Experimental data at 0.2 volt is matched exactly with the circuit on the right side. Okay. Now, I have to describe this as R solution, CDL, RP, R1 C1, R2 C2. On the right side, I will do something similar, except I will say R1 prime, C1 prime, R2 prime, C2 prime, because these correspond to different. Now, we have seen similar example before, I have just taken the circuit and put it here. When I map the kinetic parameters, I have to say K10 B1, K20 B2 are related in a particular way. For example, like this, R1 can be obtained from K10 B1, K20 B2 for a given DC. L1 or C1, I will have an equivalent relationship. That means, I need to know what is R1, L1, R0, R2, L2 or C2, and then fit the values of K10 B1, etc. Problem here is, how do I know that 150 is R1 prime and 600 is C1 prime? How do I know that 100 ohm has become 150 and 200 has reduced to 180? That is one possibility, or I can just shift this up and down. I can say 100 has become 180, it has increased to 180, and 200 has decreased to 150. You can't prove me wrong. Two circuits in parallel, I can say this is up, this is down, or this is up, this is down, both mean the same thing. That means, if I have taken data at 3 DC potentials, I can't say this resistance capacitance pair has changed to this. This might have changed to this might have changed, or the other one is also possible. So, I can't tell with confidence which combination is the correct combination, which means I can't really map it that easily. So, the problem is that we find it a lot easier to work directly with the kinetic parameter and with the experimental data. So, the strategy we would suggest is to not go via the intermediate step of EEC, although it is tempting to say that this is a elegant way of doing it. Now, a lot of people who are not familiar will say, RMA, you have so many parameters, I can fit anything. Some may claim that EEC is better because you have fewer number of parameters to do. For example, take this reaction. First reaction is electrochemical, second reaction is also electrochemical. That means, you have K10 B1, K20 B2 and gamma. and this has one adsorbed intermediate. That means you can represent it by one Maxwell element. Here I have shown you example R and L, but R and C, any of this is okay. This circuit I have given here is for Faraday component alone. This is going to be in parallel with double layer capacitance, and you may have solution resistance. We are going to say that that is common for EEC or RMA. So, we can say that you have 3 electrical elements and you have 5 kinetic parameter. If you acquire data at 2 DC potentials, you will have to represent using 6 electrical elements, 3 here, although you will show one circuit, but when you tabulate it, you have to say R1, L1, R2 at this DC, R1, L1, R2 at next DC. So, those are actually 6 variables. If you have like this 3, 4, the number of EEC elements which you vary freely, they keep on increasing. We still have the same kinetic parameters. So, we have 5 kinetic parameters to describe spectra at many DC potentials. The number of EEC elements, the circuit representation given in a figure can be misleading. You have to look at the circuit, you have to look at the table, you will see the number of EEC parameters actually more. But more importantly, the physical insight you get from the reaction is valuable. Okay. But you should not also imagine that it is valuable, but the disadvantage is it has more number of parameters. It is not easy to model many type of spectra with this. You have seen if it comes as negative impedance, it can be modeled only with a fewer type of reactions. You can't just use a simple reaction or many adsorbed intermediate, but if it does not have certain characteristic, you will never be able to model the negative impedance. So, any mechanism with many parameters cannot model any spectra, that is one thing. Second, it does not necessarily use many kinetic parameters. If you have 3 loops, which means 2 Maxwell elements, 2 Maxwell elements means 5 electrical elements, R1 C1, R2 C2 and RP. If you use 6 DC potentials, you will get 30 Maxwell elements. Even if you use 20 kinetic parameters, you are still using fewer number of parameters and you are getting valuable information. So, that is something you need to keep in mind. So, as I have shown this example before, you can map the kinetic parameters to R and L. One example to show that you should not use limited set of data to analyze and extract kinetic parameter. So, I have taken this example reaction, metal going to metal adsorbed going to metal solution, 2 plus solution, and I have taken certain kinetic parameter values K10, K20, B1, B2 and gamma, and at some DC potential I have generated data. So, it gives an inductive loop for this kinetic parameter, and I can model the Faraday component, and of course, I have used solution resistance of 0. I have used some double layer capacitance, I do not remember what that is, but let us say that we have modeled it to a circuit and I have taken only the Faraday component. I get values for resistance, inductance and other resistance here. Now, if I model this one spectrum using kinetic expression, I can get infinite number of solutions. So, obviously, the kinetic parameters I have used to generate, that is one possible solution. In addition, I have shown 2 examples, but I can get many more examples where you can verify if I take this kinetic parameter K10 corresponding B1, K20, B2 and gamma, I have in fact fixed B1. All of this combination, first set, second set, all of them will give rise to the same resistance, inductance and resistance, and will give rise to the same, because I am mapping 5 parameters to 3 elements. So, there are multiple combinations which are possible, which will give rise to the same set of elements. Whereas, if I take spectra at 2 different DC potentials, then I will not have this problem. Then I still can't tell you this is going to be a unique solution, but I can tell you there is some confidence that this is likely to be the solution. Okay. I can tell you at least it is not easy to get infinite number of solutions for the case when you have 2 DC potentials. When you propose a mechanism, okay, how do I first say how many DC potentials should I even take data and then compare? Here I have shown a mechanism where you have metal going to metal plus adsorbed, metal plus adsorbed is going into metal plus solution. Second step is a chemical reaction, first step is a electrochemical reaction. You can derive these expressions. I am not going to derive this, I will just say it is possible for you to derive and check that this is correct. Both are reversible reactions. If I propose this reaction, I should take data at certain number of DC potentials. How many should I take is the question. One adsorbed intermediate means I know that I can model with one Maxwell element in parallel with the R2. Here is charge transfer resistance. It can be RC, it does not matter. Okay. So, I can map all the kinetic parameters to 3. The way to do this calculation is this. First, find how many electrochemical steps are there. We have 2 electrochemical steps, reversible, right, that means 2 reactions. I will denote that as P. Each electrochemical step will need 2 kinetic parameters K10, B1, K minus 10, B minus 1. If it is chemical step, it will need 1 parameter each because there is no potential dependency. So, I will call the number of chemical steps as Q. So, kinetic parameter is going to be 2P plus Q plus 1 for the surface sites gamma. Each adsorbed intermediate will give me 1 Maxwell pair, and in any case I have 1 RP or RT in parallel with all this. Even if I have 0 adsorbed intermediate, no adsorbed intermediate, straightforward reaction, 1 resistance is there. Each adsorbed intermediate will add a Maxwell element. So, if I have adsorbed intermediate, it is going to be N, the total number of electrical elements present is going to be 2N plus 1. So, minimum number of DC potential I need is 2P plus Q plus 1 divided by 2N plus 1, and it may not be a integer, you have to round it up. 5 parameters to 3 potentials, we are going to say 5 by 3, it is 1 point something, we are going to say 2 potentials we need. Here you have 2 electrochemical steps, 2 chemical steps, 1 adsorbed intermediate. How many DC potentials do we need it? 2 multiplied by 2 gives you 4, plus 2 6, plus 1 7, 7 by 3, you need 3, 2 point something. Once it exceeds 2, you need 3. If you take data at 3 DC potentials, then you do not have to worry that you will get infinite number of solutions. Take it at 2 DC potentials, it is just not right to model that data with this mechanism. Okay, then I will just describe it to you. Even after I take at 3 DC potentials, I can't guarantee that this is unique solution. Reason is it is a nonlinear equation. We get guarantee for unique solution in linear equations with sufficient number of points. If I have a linear equation, set of equations, I can find the rank of the matrix and I can say that yes, so many number of variables, so many equations, therefore, I can get unique solution, or I will get infinite number of solutions, and of course, in some cases where you have inconsistent equation, you will get no solution. Nonlinear equation may give you a single solution, may give you multiple solution, and there is no guarantee. And some of them may be physically meaningful, some of them may not be physically meaningful. Okay. If we say e power minus x, you can visualize if this is y axis and this is x axis, e power minus x is going to go like this. If we say e power minus x minus sin x, I will get infinite number of solutions, because sin is going to go like this and this is going to intersect that sin x in infinite number of points. Okay. On the other hand, if we say x minus e power minus x, y equal to x goes like a 45-degree line. It is going to cut e power minus x at only one location. So, it is possible you get one solution. In some cases, it is possible you do not get any solution in real, that is also there, do not worry about that, but it is possible you get multiple solution. So, I cannot guarantee its solution is unique, but I have some confidence that it is not going to be infinite number of solutions, hopefully if I have enough number of DC potentials. If I take data at more and more DC potentials and fit properly with the model, I have more confidence that the model description is correct. Okay. So, we will stop here today.